Hi, this is Yannic from the Technion speaking, and this is joint work with Magnus from Reykjavik University and Fabian from Freiburg University. Today I will be speaking about symmetry breaking with your hands tied, or as our paper is called, Distance-2 coloring in CONGEST. Graph coloring is among the most fundamental problems of distributed computing. And by graph coloring, I mean that you want to color the vertices of the graph, so assign a color to each of them, such that adjacent vertices get different colors. And the key issues are usually how many colors do you use and how fast can you find such a coloring. Standard assumption on the number of colors for distance-1 coloring is delta plus 1, where delta is the maximum degree of the graph. Note that if you use delta plus 1 colors, then any graph has such a coloring. And it's also very easy to compute it in a centralized manner. And furthermore, even if you have some partial coloring, you can always extend it to the coloring of the whole graph. So we want to compute colorings in a distributed setting. And for this, we use one of the standard models, message passing models of the distributed world. So you have a communication network, which is abstracted as a graph. And this is the graph that we want to color. We want to compute the distance-2 coloring of this graph. I will later tell you formally what this means. And to color the graph, the nodes communicate in synchronous rounds. So in one round, they can send messages to each other through the communication edges. So you can send messages to your neighbors. You can perform some local computations. Here I want to point out that a node can send different messages to different neighbors. So it's not a broadcast congest model. And the messages should be small. So small means usually in the order of log n bits. And at the end, each node only has to compute its own part of the solution. So it has to announce its own color. The complexity measure here is the number of synchronous rounds that you take until everyone has computed its own color. So what is known about coloring distance in this CONGEST model? And here I'll first focus on distance-1 coloring. So I think it's folklore, and it also appears in several papers, and we will talk about this algorithm in more detail later, that you can compute the delta plus 1 coloring randomized in order of log n rounds, a distance-1 coloring. If the graph is sparser, you can do it faster. There you can do it in order of log delta plus polylog log n rounds, as shown by Ghaffari in SOLA 2019. There's another paper here from last week which actually improved this polylog log n term. This is why two papers are here. So this algorithm is based on shattering and network decompositions and more. If you want to look for deterministic algorithms, then there's another paper at this year's PODC, which shows that you can also compute delta plus 1 colorings deterministically in polylog n rounds. So this essentially meets the same has the same runtime as we have in the local model. What we want to do in this talk here is distance-2 coloring. So in distance-1 coloring, we want to assign each node a color such that neighbors get different colors. In distance-2 coloring, we want to assign each node a color such that distance-2 neighbors get different colors. And what is a distance-2 neighbor? It's a node of distance at most 2. So here I want to emphasize that it's at most 2, not exactly 2, it's at most 2. So what we want to do here is we actually want to color the square graph of the communication graph. So this communication graph itself stays G. This is the communication graph, but we want to color G squared. Another equivalent formulation of this problem is that you want, if you look at one vertex, that all of its neighbors receive different colors. For the number of colors, we're aiming at delta squared plus 1 coloring, because this is equivalent of delta plus 1 coloring for distance-1 coloring. Maximum degree of G squared is delta squared, or can be delta squared. The goal is to compute this fast. And we want to do this in the CONGEST model. Note that if we're in the local model, so this is like the CONGEST model, but you don't have this bound on the message size, then this D2 coloring problem is not more difficult asymptotically than the distance-1 coloring problem, because you can just simulate an algorithm that was designed for D1 coloring just on the G squared with 2 rounds overhead. So why are we interested in distance-2 coloring? And the most well-known motivation comes from wireless networking. if you're in a wireless network, you want to make sure that two nodes that communicate and send some messages in the same time step, they should not share a common neighbor. Because if they have a common neighbor, it cannot hear properly if they send on the same frequency in the same time step. Of course, to make sense of our results, you need to separate a higher order model to first compute, like a CONGEST type model, to first compute the distance-2 coloring, to later use it for scheduling purposes in your wireless network. Another motivation, and this actually brought us to studying this problem, is for de-randomization of one-round algorithms. So if you want to de-randomize in a distributed setting with a method of conditional expectation, and you have a one-round randomized algorithm, you very quickly realize that distance-2 colorings are very helpful for this. Another relation is from coloring hypergraphs. But yeah, what we find is pretty interesting is that the problems that occur here in this setting capture a more constrained or different model of communication. To explain this, see, in the CONGEST model, every vertex can talk to all of its neighbors, and you can send different messages to each of the different neighbors. This is not the case here in the D2 setting, distance-2 setting. You cannot send an individual message to each of your distance-2 neighbor. The communication has to always go through a distance-1 neighbor. So basically, this distance-1 neighbor is a relay, and all the communication has to go through this relay. So let's look at what can we say about distance-2 coloring. First of all, verifying that a given coloring is a distance-2 coloring is easy. You just let each node send its color to each of its immediate neighbors. And now if a node receives the same color twice, it's not a valid proper distance-2 coloring. If this is not the case, it will be one. In contrast, learning the colors of your D2 neighbors is hard. Because, well, you might have up to delta squared D2 neighbors, but you only have delta incoming edges, so you can only learn delta colors at a time. So it takes delta rounds to learn them all. And then if you go beyond distance-2, if you go to distance-3 coloring, then even verifying a coloring is hard. And this follows from standard reductions from communication complexity with the LS-Bob framework and the set disjointness function. So in this setting, to verify that the coloring is a proper distance-3 coloring, you need that the colors on the left-hand side, Alice's colors, and the colors on the right-hand side, Bob's colors, are disjoint. So this is very much like the set disjointness function. What we have in this paper are algorithmic results on computing distance-2 coloring. First result is the log delta times log n randomized algorithm to color with delta squared plus 1 colors. Second result is a deterministic algorithm, which runs in polylogarithmic time, but uses slightly more colors. It has a small constant fraction more colors that it uses. And we have an order of delta squared plus log star n algorithm, which colors with delta squared plus 1 colors. I will today in this talk mostly focus on the first result, but I quickly want to say two things about the other two results. So let's begin with the second one. This is based on the de-randomization of a simple zero-round randomized algorithms, which comes from a two-color splitting problem of a previous paper. And if we apply this de-randomized algorithm recursively, then what we obtain a partition of V of the vertex set of the graph into smaller parts. And now we would like to use a distinct color space for each of these parts. And the problem that we compute here, this de-randomization process, is designed such that actually on all the parts and all the graphs induced by these parts, we can communicate in G squared as efficiently, just with some small overhead, as if G squared itself was the communication graph. Like, this is everything I want to say about this. For more details, look into the paper, in the full version of the paper. And the third part is just an efficient implementation of the deterministic algorithm of Barenboim, Elkin, and Goldenberg from PODC 18, for those who know this one. If you don't know it, you should get familiar with the algorithm. It's a very nice, cute algorithm. So for the rest of the talk, I want to focus on this result on randomized coloring in order of log delta times log n rounds with delta squared plus 1 colors, distance-2 coloring. So first, let's revise this basic randomized coloring algorithm for distance-1 coloring. So this has log n iterations, and in each iteration, each node picks an available color. An available color is a color that is not used by an already colored neighbor, and it just picks such a color at random. If no neighbor also picked the same color in the same round, then you use it, and afterwards you update the set of available colors. It's a nice exercise to show that in this process, each node is colored with a constant probability in each iteration. So you're done after order of log n iterations. But the bad news here is that this doesn't work for distance-2 coloring, simply because a node cannot learn which colors have already been used by its neighbors. So instead, what we could do is actually do the even more naive algorithm where you just try an arbitrary color at random and don't update the palette of available colors. So you try an arbitrary color, and if no D2 neighbor also picks it, then you use it. The good news is that this works very well if you have enough colors. And enough colors just means you need a constant factor more than delta squared colors. So the 2 down here can be replaced by any constant factor larger than 1. The bad news is if you really don't have this constant factor and want to go down to delta squared plus 1 colors, this takes forever. So what has been observed now before is that this process actually works well if your local neighborhood is sparse. And by sparse, what I mean is that a constant fraction of the edges that could be there in this D2 neighborhood. So a constant fraction of the pairs of edges that could be there between D2 neighbors are actually not there in the graph. So in the very extreme case, it would look tree-like. And the intuition is then that, and this was observed before by Petty and Su, that after one iteration of this algorithm, you already get that many of your distance-2 neighbors are colored with the same color. And then what happens in our papers, this becomes like coloring with a palette of size 1 that is a constant fraction larger. So the most difficult case is actually the dense case. And here let's look at the very extreme case that your neighborhood in G squared is actually a clique. And so let's focus on the setting where actually all the vertices, all your neighbors are already colored. Just this node V is still uncolored. So in this case now, this node V only has a single color that it can actually take. And now if it just by itself tries to just uniformly at random pick a color from all the colors, then it will take a very long time until V is actually colored. On the other hand, all these nodes in the clique there, they're already colored. They have nothing to do. So our key idea here is that we just ask the friend to help to color them. And everyone in the clique tries to help V to get colored. So everyone will also try random colors and will try to figure out whether the color is helpful for V. If it is helpful, we'll say, suggest to V and say, hey, how about you try this color? And because actually here in the clique, all these other vertices see the exact same neighborhood as V, they can very easily figure out whether a color is helpful for V or not. So with constant probability, at least someone in this clique will guess the missing color, verify it, and suggest it to V. So this works from the start in this extreme case that your graph is a clique in G squared. Does this easily extend to the general setting, to general graphs where you don't have this extreme case? It turns out that it's not so easy, but our idea here is still the same. So each colored node U tries to help help a random live D2 neighbor. So a node is live if it's still uncolored. And how does the node U now help? It tries random color C and tries to figure out, is this color C good for myself? Because this is a good indication that it's also good for V. If we are in dense part and see roughly the same neighborhood. And then if the color C is good for node U, it will forward it to V and say, hey, here, how about you try this one? And then V tries some of these proposals. So this works like a filter, because other nodes try to filter out colors which we shouldn't try, and it will only get some number of proposals. But this filter comes with errors. So to see this, let's look at an example. So we are in this setting. This node V is uncolored, node U wants to help, and they have some common neighbors. These are the vertices at the bottom. But now there could be false positives, because it could be that U tries color green and checks, hey, green is a great color for me. Probably it's also good for V. Then it forwards it to V, but V already has a green neighbor. So this is really not helpful advice. And there are also false negatives, because it might be that U guesses color red and checks, is red good? And figures out, no, red is not good. I have a red neighbor, so I will not suggest that to V. So these two types of false positives and false negatives can happen if we're not in the extreme case of a clique. And what we try to do is we try to have these false positives and false negatives as few as possible. And now I will become a bit hand wavy, but try to give you the intuition of what we do here. So the first idea, and this is helpful for actually both of these settings, is that we only ask similar neighbors to help. Similar means that they almost see the same D2 neighborhood, except for a small constant fraction. So because if they almost see the same D2 neighborhood, then most of these verifying tests for the color C themselves will be the same as for node V. But this doesn't help us to go around these false negatives, because if the node U will never suggest this red color, because the test will always be negative. And for this, we have to enhance a second idea. And the second idea is that we also suggest some random color in our D2 neighborhood. If we know that this node is not a D2 neighbor of V. And this, in this example from before, would, for example, exactly suggest this color red. So let's look at this algorithm again with an animation. So we have this live node V, and some other node U says, which is already colored, says, hey, let me help you. So this is a D2 neighbor. So yeah, this is actually a D2 edge here. And then it just wants to try a random color for V. So it tries a color, and then it checks, hey, does blue work for myself? And for checking this, it has to correspond and communicate in the graph G actually quite a bit. And if this color blue is good for itself, then it proposes it to V. This is the first type of help. And the second type of help is, yeah, let me take one of my D2 neighbors and figure out, hey, are you a neighbor of V? Like a D2 neighbor of V? If not, so then I will also send your color and suggest it to V. And the key claim is that one of these two types of help actually is good for V and works with, has a good success probability. So let me briefly, in a simplified version, summarize the whole algorithm. So first of all, everything what I explained right now uses that we know which vertices in the graph have similar neighborhoods. So at the very start, we form a so-called similarity graph H, in which we compute which vertices have similar neighborhoods. This is also a randomized process that works with high probability. to figure out this graph age. And then we first color all the sparse vertices, as I explained, just with this simple color guessing algorithm for log n rounds. And then we color dense nodes with this helping hand ask a friend algorithm. And for this to work, we actually need a lot of concentration bounds. And all of these fail once the uncolored degree drops below log n. So once the degree of uncolored vertices is too small, we need a different finish off phase. I won't go into detail and didn't talk about this finish off phase today at all. For this, please, check out the paper. So let's also recap this helping hand algorithm. So this one repeats for log n iterations. The already colored vertices, they decide which live neighbor, similar neighbor could I help, selects one, and then you just pick a random color and check whether it's good for yourself. If it works for yourself, you suggest it to the other node, who can then see, is it really a good, helpful advice? If not, you discard it. If it's helpful, it's going to be colored. And you also have the second type of advice, where you try, this is what, to battle this, that the red color will never be suggested in this first type of advice, where you just pick a random color that is used by one of your neighbors and suggest this one as help to the node V. So now all of this looks like our runtime should only be log n and not log n times log delta. But actually, these arguments here, we could only prove them in this case if the sparsity level of all the vertices that are uncolored actually is roughly the same. So around this helping hand, we have another loop which iterates to all the levels of sparsity. And this is log delta levels. This is why we get the log delta times log n algorithm here. So let's conclude what we have here. So this distance-2 setting captures one form of computation and constraint communication. And the standard approaches that we have for coloring algorithms don't really work, but one can still perform some algorithmic treatment to actually get something done. And I think it's a rather unusual approach that we have here, like that vertices don't just try to get colored by themselves, but you have other nodes which act as a filter for you. So it's not purely collaborative, but you have nodes that help as a filter. So there are follow-up results on this paper which appear at disk, where we basically got rid of this additional log delta factor. But since it's technically a bit involved, I won't go into any details on how we got this here. And since we also made this amendable to the shattering framework, now actually this distance-2 coloring matches the best known bounds that we know in the CONGEST model for distance-1 coloring. So these improved results are the same author as this paper and one more author, Alexander Nolan. So there's still lots of open questions here. So first of all, what I didn't put on the list here is one can study these relay networks for other problems. And these models are very interesting, I think. But then also our algorithm doesn't do degree plus 1 coloring, where degree is the degree in G squared of a node. It can be much, much smaller than delta squared. What about list coloring? What about lower bounds? Lower bounds we don't have any pretty much except for the log star, and which even holds for in the local model for distance-1 coloring. So yes, and many of these questions randomized, I think, are not even resolved completely for distance-1 coloring. So the big open question, when can we color fast, remains.